Hello again. I'm Gülay, and the paper that I'll present today has this long name on the screen, using Boolean functions of context factors for adaptive mental model aggregation in organizational learning. This is our second paper with Jan Truer, and in the beginning, I will explain some common things as in the previous slide presentation. It will be like a memory refresher for those who listened to the previous one. When we talk about mental models, three concepts come to our minds: usage, adaptation, and control. Having knowledge or even having only an image of a thing or a task or an abstract concept is the usage of mental models. We have the inner representations of the outer world in our minds. And adapting these representations means gaining or losing knowledge on them. Learning is the strengthening the connections of the mental models, and forgetting is the weakening them. And of course, we have the ability to control this adaptation, for instance, by doing mental exercises. Controlling is mainly about the speed and persistence of the learning and forgetting. On the other hand, organizational learning is an interesting process of unification of individual mental models. These four are not strictly separated states, but we can consider organizational learning as a process that consists of four different phases to see the change and the progress easily. First one is individual learning of persons. Here, individuals improve their mental models. And the second one is formation of shared organization mental model. Here, individuals create their shared mental model. It's called feed-forward learning. And in phase 3, individuals start to learn from their shared mental model. It's a feedback learning from organization to individuals, and it's called instructional learning. And the last phase is the improvements of individuals with the help of their learning from their shared mental model. And the main focus of this paper is the Boolean functions used to control aggregation of the individuals in this second phase. We use different functions and context states, but I'll talk about in detail them later. This is the cognitive architecture for mental models, and we have equivalent layers for this cognitive architecture. The left ones are the cognitive architecture layers, and the right ones are the self-modeling network layers. For usage, for internal simulation, we have base level. For adaptation, we have first order self-model level, and for control of adaptation, we have second order self-model level. This is the self-model network, self-modeling network for feed-forward learning. In this base level, we have mental models for individuals. These are for person B and these are for person A. And also we have base level mental models for organization that didn't exist in the beginning. For all these connections, we have W states representing the weight of the connection. For example, for this connection from A to B, for person B, we have this W state. We have 3 different W states for each person and also the organization. And also we have connections from W states to W states to make organizational learning possible, these connections. And also we have for feedback learning, the opposite connections. We have the opposite connections from organization to individuals. These are needed to make persons, individuals able to learn from their shared mental model. And as I said, we have 4 different phases. Therefore, we have 4 different context states here. These context states are like the switch between the phases. As I said, the base level is here, and this is like the core of our model. And in this first order self-model level, we have W states, and we have also these context factors. These are needed to determine the context, the case, because our model is context sensitive. It's depend on the context. We have a lot of context states. And also in the second order self-model level, we have aggregation control states, these C states. And also we have H states for speed factor, M states for learning persistence, higher order W states for the W to W connections here, feedback and feed-forward learning. These C states are here to make the aggregation of individual mental models adaptive. The aggregation part takes place with the help of the combination function. Therefore, these C states represent different combination functions. We have 4 different combination functions: logistic sum, scaled maximum, Euclidean, and scaled geometric mean. And we have 3 kinds of connections, these A to B, B to C, and C to D. Therefore, 3 times 4, we have 12 C states in total. And also, as I mentioned, we have context states to determine the choice of the combination function. We have a context state for knowledgeability, for dependency, and for the preference for type of quantity. For example, if the case will be the following, A and B are both experienced, they are dependent on each other, and their preference is additive. If this is the case, the function will be Euclidean, will be selected as Euclidean. When we use zeros and ones to see the things clearly, we got this table. And if this table is carefully examined, we can extract Boolean prepositions for these functions, as you can see in the next slide. For example, for C1, for the state C1, representing logistic function, this is the Boolean preposition. It says if A is experienced and B is experienced and they are not dependent on each other, the function will be logistic. When we look at this table, we can see that this is correct. A and B both experienced, they are not dependent, then the function is logistic. The other Boolean prepositions for the other functions are there. And to get rid of this negotiation notion, we just created the opposite of these states, these context states. For experienced states, we have beginner states. For dependent states, we have independent states. And for additive preference, we have also multiplicator preference. And this is the final version of our Boolean prepositions for functions. And of course, we need connections from these context states to C states, because context states determines the case and affects the C states. The combination function is selected according to the case itself. And required connections, we can see the required connections in this table easily. These are the context states, these are the C states. And for example, again, for logistic function, for C1, we need connection from experienced A, experienced B, and independent AB. We have double plus for preference states, because when we look at the prepositions, we can see that we just used them twice. And here, the order is also important. We should keep the order here. These states also need a combination function, and their combination function has a form like this. It's not a complicated function, but because it will take time, I won't explain it right now. But if you want me to explain, you can ask after the presentation. This is our simulation result of our first scenario. In this first scenario, we used Boolean values for context states, as you can see in this next slide. The context states are either 0 or 1. Therefore, our combination function selection has done in the beginning. Here, the purple one and the black one are the C states, and the selected C state is C2, according to the case. The other part is the classical organizational learning. These are the phases. This first phase, individual learning. The second phase is the formation of shared mental model. Here is learning from the shared mental model, and this fourth one, the last phase, is the improvement of individuals. In the second scenario, we just use non-binary values for context states. It was binary in the previous one. Here we have values like 0.9, 0.4, 0.5 or something. And therefore, our combination functions are not 0 or 1. More than one combination function is selected here. And the software takes the average of them. Therefore, the aggregation of the individuals, the formation of the shared mental model is different here from the first one. The learning levels are different because the different combination functions are used here. In this third scenario, we again used binary values for context factors. They are still, again, 0 or 1, but in this time, we changed the context at 400. With the help of step 1 function, we have a context here, we have a case here, but after 400, we changed our context, as you can see here. Therefore, the combination functions are also changed according to the changing context. And our last scenario is again on the changing context scenario, but for this time we use non-binary values for context states, like in this second scenario. We have non-binary context values. Therefore, our combination functions are different and our learning levels are different, but the idea is same. After 400, the context is changed. Therefore, the combination functions are also changed. Thanks for listening. If you have any question, you